Okay, so next we're going to talk about Venn diagrams, which is a useful way of graphing the relationships between different sets. And you may have seen this before previously, but it's helpful to review it now because it's extremely helpful when we start talking about complicated situations in order to see the different possibilities that are possible for subsets. So for a Venn diagram, what we can do is we can think of first drawing a box for the so-called universal set, which in this case we can think of as our sample space S. And then if we have subsets within S, then we can draw them as blobs. So let me just draw a single subset, A. Okay. So this is a simple Venn diagram for a single set within a subset, within a universal set. If you want to think of coloring the sets, I can think of, well, that color there is that showing up? I guess okay, it's visible. That color there is the coloring for the inside of A. If I wanted to think about a complement is the set of all elements, outcomes that are not in A. That would be the space outside of the blob for A. So that was A. I'll draw it. That's A there, and then this space outside of A corresponds to a complement. So basically we can use Venn diagrams to divide the universal set or sample space into different pieces, and then each graphical section has an interpretation in terms of intersections or complements of sets. So that's very simple. Let's see what can happen if we have two subsets. So I'm going to have one subset A, I'm going to have one subset B. So if I'm drawing it like this, then I am showing that these two sets have an overlap. Now, this divides the sample space S into four different pieces. So we have this piece out here, we have this piece here, we have this piece here, we have this piece here, as well as, of course, the pieces that correspond to B and A. So if we wanted to, we could think of showing the specific descriptions in terms of intersections and complements for each of these different pieces, and this is quite helpful. So this set here, this is the set that is in A, but is also in B. So this shaded region corresponds to A intersection B. Okay? So if I redraw the picture now, that's A and that's B. If I think of A union B is the set of all things that are in A or in B, and A union B would be this entire space here. Okay, so the simple Venn diagrams, we can identify A intersection B and A union B. So what's really helpful is to be able to go further than this. If I wanted to identify this space out here that is not in A and is not in B, how could we do it? Well, that space out there is a set of things that are not in A union B. So it is A union B complement. So if I shade everything here, I hope you can see that what I'm shading in this picture exactly the parts that I did not shade in here. So that is the complement. So this region here is A union B complement. Okay, now another important thing to be able to specify are parts of this diagram where you have parts that are belonging to one set but not belonging to the other set. So to build up how we can do this, let's note the following. So I'm gonna stick with this basic diagram here. We're gonna have A over here, and B over here. So first note that I could write A complement would be everything that is not in A. So this set here is A complement. Now, if I want to describe the part here, that's just this half moon part, that is the set that is elements that are in B, but are not in A. And I can also write that as saying that is the set of elements that are in B and are in the complement of A. So this set here is B intersection A complement. So this is going to be an important, you're going to have to get familiar with being able to identify these types of pieces on a Venn diagram. So similarly, this section here would be A intersection B complement. Okay. We can have Venn diagrams with more than just two subsets, and this can get more complicated, but I'll just show the sort of general picture and talk a little bit about it. So I could think of a situation where I had universal set S and then three overlapping subsets, A, B, and C. And then the different possibilities for where they overlap divides the set into different regions, which you can see clearly on the Venn diagram. So I'm not going to keep redrawing this figure because it's going to take too long. But let's just think about the following. So what is A intersection B intersection C? If you were to draw in this region or shade in this region on the Venn diagram, where would it be? Well, A is this set here. B is this set here. So A intersection B is this set here. And then if you take the intersection with C, it says it's the set of elements that are in A, in B, and in C. So this is that. right there. So that A intersection B intersection C refers to just that little region there. Okay, so it's a little bit more complicated now. How could I specify, for instance, just this region here? Well, what am I drawing here? I'm drawing what am I shading here? I'm shading the part of A that is in A, that is not in B, and is not in C. So similarly to what we did before, we could think about this region here as being A intersected with the things that are not in B, so that's with intersect B complement, intersected with C complement. So A intersection B complement intersection C complement is going to give us just this piece right here. So this is saying things that are in A and in not B and in not C, which refers to this. Okay, so what about another thing? How can I describe this set right here? Okay. Well, what's happening here is these are the elements that are in the set B, are in the set C, but are not in the set A. So I can describe that as B intersection C intersection A complement. So that's in B and C, not in A, would be this section right here. Okay. I think I'll leave it at that. But you should study and become familiar with different ways of describing different regions. Let me conclude by this. How can we describe the elements that are in two of the subsets, A, B, or C, but not in all three? This is a little bit more complicated. So the set there that I'm talking about would be the set of elements that are in two, but not in all three. So that's going to be this piece, union this piece, union this piece. So if you think about how to write that out, similarly to here where we had B and C and not A, describe just this piece. This piece here is going to be A and B and not C. And this piece here is going to be A and C and not B. So if I wanted to describe the set of elements in two of A, B, or C, but not in three, this would be A intersection B intersection C complement, which would give me that piece, union A intersection C intersection B complement, which would be that piece, union, this thing we just described, B intersection C intersection A complement. So that would be the set that looks like that, if I described it that way. Okay. Finally, if we have a set that is disjoint, then we have a Venn diagram that looks as follows. We can draw a Venn diagram that looks like this, just to show that A and B do not have any elements in common. Okay, I'm going to conclude this by walking through a description of De Morgan's laws. So it's not especially important that you remember that these are called De Morgan's laws, but these are statements about set theory that you should become familiar with. So what this says is the following. So A union B, A intersection B complement. De Morgan's law is a way of taking this statement about intersections and turning it into something about unions. So it's easier to see what's happening if we draw the Venn diagram. So if I have A there and B there, then A intersection B complement is the set of all the elements that are outside of that intersection there, right? So this section here is A intersection B. A intersection B complement is everything outside of here. So let me just draw what that is. If I think of A complement is everything that is outside of A. And if I think of B complement is everything that is outside of B. So the intersection of, the union of A complement and B complement is actually going to be equal to this set as well. So this is the first of the so-called De Morgan's laws. So we have this statement about set theory. So maybe now that I'm thinking about it, I should draw out these more explicitly. So this set here I'm shading everything that is outside of A. That set is A complement. And this set here is everything that is outside of B is B complement. And this set here, which is everything outside of that intersection, is what I started with, A intersection B complement. So the first of De Morgan's laws is saying I can describe this set as well by saying it is this set here union this set. So if you take all the points in this set and include all the points in this set, basically what's going to happen here is all of these red points, if I bring them over here and overlay them here, it's going to fill in everything that's in B that's not in A, because this doesn't include anything in A. And so this set is equal to the union of these two sets. So this also has an interpretation in terms of logic. So if I go back to the linguistic interpretation of these, this is A and B not. So this says not A and B. Whereas this says not A or not B. So it's like if A and B are two events, how is it possible that not A and B occurs? Well, if if not A doesn't occur, then not A and B didn't occur. Or if not B doesn't occur, not A and B doesn't occur. So I guess I don't want to confuse the point too much. But there's if you think about the linguistic interpretation of this and this, you can also have another understanding of where De Morgan's laws are coming from. And maybe some of you have studied digital logic as well. This also comes up in digital logic. Okay, so I'm probably taking too long on this. The second of De Morgan's laws is this. If I say A union B complement, let me erase that and then try to show what the Venn diagram picture looks like for those. So I'll have A, B, it's my Venn diagram. So A union B is the set where I'd fill in both this circle and the intersection as well. And the complement of that is everything outside. So this set here is A union B complement. Right? So the inside is A union B, and then the outside is A union B complement. And so this second law has an interpretation where I can express this in terms of A complement and B complement. So let me write those out, or shade those out. So I'm going to again write A complement here. That's the set A complement that I've shaded. And then I can shade this set. Which is B complement, everything outside. This is B complement. And the statement is that, all right, how can we take this set and combine them in a way to produce this set? Well, if you think about it, it is that everything that's red here and red here is going to be what I want over here. So these parts are, this thing that's outside of both A and B is marked red here and here. In this one, this part inside of B gets marked red, and I don't want that to be marked here. But if I take the intersection of these two sets, I'm going to exactly get this picture here. So hopefully this is clear from my somewhat artless shading. I apologize, I'm a math major, not a graphic design major, so my shading is maybe not perfect. So the interpretation here is that union B complement can be written as A complement intersection B complement. And again, this has a linguistic interpretation. If I say this, think about this, this is not A and B. So how can it be possible that it's not true that two events occur? Well, that means that the first event did not occur, and also the second event did not occur. So this is the same as not A and not